Welcome back to Chapter 4 of Principles of Mathematical Analysis. In the last section, we paired continuity with compactness and found that continuous maps preserve compact sets. In this section, we tell the matching story for connectedness. The headline result is just as clean. A continuous function sends connected sets to connected sets. From this single fact, we will recover one of the most famous theorems in all of calculus, the Intermediate Value Theorem, which says that a continuous function on an interval takes every value between any two of its values. Finally, we will look carefully at whether this theorem has a converse and discover a surprising answer. Let's get started. Here is our plan. We open with some motivation, what connectedness means and why preserving it matters. Then we prove the main theorem, that the continuous image of a connected set is connected. From it, we derive the Intermediate Value Theorem for continuous real functions on an interval. We close with a remark that examines a tempting but false converse and a summary of the key ideas. Let's set the stage. In the previous section, we proved a structural theorem. If you push a compact set through a continuous map, the image is still compact. That was our first example of continuity preserving a topological property. It is worth pausing on that idea because it is a recurring theme. Next, we will see that the very same thing happens with connectedness. So a natural question presents itself. Compactness is one major property of sets from Chapter 2. Connectedness is the other. If continuous maps respect compactness, do they also respect connectedness? In other words, if the domain is in one piece, must the image also be in one piece? The answer, as we will prove, is yes. And the reward for answering yes is substantial. The fact that continuity preserves connectedness is exactly what makes the Intermediate Value Theorem true. That theorem is the rigorous version of an intuition everyone has from calculus. If a continuous function starts below a level and ends above it, then somewhere in between it must hit that level exactly. Let's now make all of this precise, starting with a quick reminder of what connected means. Before the main theorem, let's recall the definitions from Chapter 2. Two sets are called separated if neither one contains a limit point of the other. Formally, A intersected with the closure of B is empty, and the closure of A intersected with B is empty. Notice this is stronger than just being disjoint. Disjoint sets can still touch at a boundary point, but separated sets stay genuinely apart, closure and all. For example, the two open intervals from 0 to 1 and from 1 to 2 are separated, because neither one reaches the point where they would meet. But if we close up the first interval to include that meeting point, they are no longer separated. A set is then called connected when you simply cannot break it into two non-empty separated pieces. Intuitively, a connected set is all in one piece. With these definitions fresh, we are ready for the main result. Here is the central theorem of the section. Take any continuous map F from a metric space X into a metric space Y. If a subset E of the domain is connected, then its image F of E is also connected. The picture captures the idea at a glance. On the left, in blue, sits the connected set drawn as a single unbroken blob inside X. The orange arrow is the continuous map F. On the right, in red, is the image inside Y. Notice that its outline is drawn quite differently from E, and that is on purpose. A continuous map is free to stretch, bend, or squash a set in almost any way. The one thing it can never do is rip a connected set into separate pieces, so no matter how badly the shape is distorted, the image stays in one piece. That single idea, that continuity never tears a set apart, is the whole content of the theorem. Let's prove it. Before the formal argument, here is the roadmap. We argue by contradiction. We start by assuming the conclusion fails, so the image f of E can be broken into two non-empty separated pieces. Call them A and B. The key move is to pull this break back through F to the domain, producing two pieces, G and H, of E. We then check that G and H together make up all of E, and that neither is empty. The heart of the proof is using continuity to show G and H are themselves separated. But that would break E into two separated pieces, contradicting the assumption that E is connected. Let's walk through each step. Step 1. Suppose, for contradiction, that the image is not connected. Then we can write f of E as a union of two non-empty separated sets, A and B, living in Y. In the picture on the right is the image f of E, the same deformed shape from the previous slide, but now broken into two red pieces that stay apart, A and B. Now we pull this decomposition back into the domain. The blue set E on the left. Define G to be the points of E that F sends into A, and H to be the points of E that F sends into B. The dashed line inside E marks this division. In symbols, G is E, intersected with the preimage of A, and H is E, intersected with the preimage of B. The orange arrow is the map F, carrying G to A and H to B. Next, we check these pieces behave well. Step 2. Because every value of F on E lands in either A or B, every point of E belongs to G or to H. So E is the union of G and H, and since A and B are each non-empty, and they are both actually attained as images of points of E, the pullback sets G and H are non-empty as well. So we have genuinely split E into two non-empty pieces. The only thing left to check, and it is the crucial thing, is that these two pieces are separated. Step 3 is where continuity does its work. Start with the obvious fact that A is contained in its closure. Taking preimages, G is contained in the preimage of the closure of A. Now here is the key point. The closure of A is a closed set, and the preimage of a closed set under a continuous map is closed. We proved that characterization of continuity earlier in the chapter. So the preimage of the closure of A is a closed set containing G. Therefore, it must also contain the closure of G, since the closure is the smallest closed set containing G. Applying F, we conclude that F of the closure of G sits inside the closure of A. Let's use this. Step 4. Recall that F maps H onto B, and that A and B were separated, so the closure of A does not meet B. Now suppose a point lived in both the closure of G and in H. Its image would lie in the closure of A from the previous step, and also in B, because it is in H. But the closure of A and B are disjoint, so that is impossible. Therefore, the closure of G and H share no points. Running the exact same argument with the roles swapped shows G and the closure of H are also disjoint. By definition, that means G and H are separated. And now we collect the contradiction. We have written E as the union of two non-empty separated sets, G and H. But that is precisely what cannot happen for a connected set. Since we assumed E is connected, our starting assumption that the image could be split into separated pieces, A and B, must have been false. Therefore, F of E admits no such split. It is connected. That completes the proof. Notice how little we used, only that pre-images of closed sets are closed. Now let's cash this in for the Intermediate Value Theorem. Here is the famous consequence. Let f be a continuous real-valued function on a closed interval from a to b. Suppose the value at a is less than the value at b, and pick any number c strictly between those two values. Then the theorem guarantees there is some point x inside the open interval where f of x equals c. In plain words, a continuous function on an interval cannot skip any value between two of its values. It assumes every intermediate value. Of course, the same holds if the function is larger at a than at b. Just reverse the inequality. Let's see the picture, and then how cheaply this follows from Theorem 4 Tone 2. Let's read the diagram. The blue curve is the graph of our continuous function f over the interval from a to b. On the left, it starts at the height f of a, and on the right, it ends at the higher height f of b. The horizontal orange line marks the target level c, chosen somewhere between those two heights. Because the curve begins below the orange line and ends above it, and because it is unbroken, it has to cross the line somewhere. That crossing is the red dot sitting above the point x on the axis, where f of x equals c. The function might wiggle and cross several times, but the theorem only promises at least one crossing. Now, the proof. The proof is remarkably short, and it sandwiches our new theorem between two uses of a Chapter 2 result. Step 1. By Theorem 2.47, the closed interval from a to b is connected. Step 2. Feed that connected interval through our continuous function and apply Theorem 4.22, which we just proved. The image is a connected subset of the real line. Step 3. Apply Theorem 2.47 in the other direction. It says a connected set on the line has no gaps. Whenever it contains 2 points, it contains every point between them. One subtle point worth stressing, shown in the gray box. This does not force the set to be a closed interval. The boundary points may or may not belong to it, so the image could be open, half open, or closed. That does not matter here, though, because all we need is that the image contains f of a and f of b, and therefore every value c strictly between them. So some point maps to c. Done. Here is a natural and tempting question. The Intermediate Value Theorem says continuity implies the intermediate value property. Does the arrow run the other way? That is, suppose a function f has the intermediate value property on every subinterval. For any 2 points x, 1 and x, 2, and any c between the corresponding values, the function actually hits c somewhere in between. It feels like such a function should be forced to be continuous, since it never seems to skip a value. Let's see whether that intuition holds up. The answer is no, and the counterexample is a function we will meet again. Example 4.27 Part D. Define f of x to be the sine of 1 over x away from the origin, and 0 at the origin. As the picture shows, near 0, this function oscillates faster and faster between -1 and 1, packing in infinitely many wiggles. Because of those oscillations, on any interval touching the origin, the function sweeps through every value between -1 and 1. So it does have the intermediate value property. Yet it is wildly discontinuous at the origin, since it has no limit there. The left and right-hand limits simply do not exist, so the intermediate value property is genuinely weaker than continuity. The converse fails. Let's gather what we learned. The first and central result is Theorem 422. A continuous map carries connected sets to connected sets. Just as continuity preserved compactness in the previous section, it preserves connectedness here. The proof was a clean contradiction argument, pulling a hypothetical split of the image back to the domain, and using only the fact that pre-images of closed sets are closed. The second takeaway is the celebrated payoff, the Intermediate Value Theorem. A continuous real function on a closed interval takes on every value between its endpoint values, and the proof was almost free. Sandwich Theorem 4.22 between two applications of the Chapter 2 fact that connected subsets of the line are exactly the intervals. This is a beautiful example of how a general topological theorem yields a concrete classical result. The third takeaway is a cautionary one. It is tempting to believe the intermediate value theorem has a converse, that the intermediate value property forces continuity, but it does not. The function sign of 1 over x has the intermediate value property near the origin yet is badly discontinuous there. So continuity is strictly stronger. That naturally leads into our next section on discontinuities, where we classify the different ways a function can fail to be continuous. Thanks for watching, and see you in the next section.